In this example, our order states we have 1,000 ml of normal saline, and in this normal saline we have 15 milliequivalents of KCl, which is potassium chloride. We need to determine at what rate in milliliters per hour that this bag should be running so that the patient is receiving 4 milliequivalents per hour. Now, there are a few new things in this example, one of them being this idea of MEQ, Milli Equivalents. So I can spell that out. And you see the prefix here, milli, that is equivalence. Milli is it's a metric system, and it's talking about 1/100th or 1/1000th, excuse me, of an equivalent. And equivalence is just a way to measure compounds and biological compounds, and we don't want to say it's a mass, it's not a volume, it's a particular way in chemistry that we can measure the amount of chemical compounds and biological compounds. And in this one we're talking about potassium chloride. It's common when we are talking about electrolytes. And when we say we have a bag of NS with 15 milliequivalents of KCl, that's telling you the strength of this bag. It's telling you there are 15 milliequivalents per 1,000 ml. And that's important, obviously. You can think of that almost as milligrams per ml. It's the strength, but it's not milligrams, it's milliequivalents per ml. In these problems, a lot of students will start with that and try to arrive at milliliters per hour. But that's not the preferred method. It's not that you can't arrive at the answer or the correct value using that method, but it's a little bit easier to think about these problems in terms of what does the patient need to be, what needs to be happening with that patient? What do they need to be receiving in this example? And although it says order 1,000 mLs, 15 milliequivalents, what really needs to happen is this piece right here. The patient needs to receive 4 milliequivalents every hour. But as we see in the picture over here, we have these milliequivalents floating around in this bag. They're going to be hooked up to a pump, and it's going to be that pump that is pushing the liquid. So what we need to do is actually set the pump in milliliters per hour. So the patient must be receiving 4 milliequivalents every hour. So I'll start there by writing that rate. That is a rate. This is a rate conversion. We are converting a rate of milliequivalents per hour into, when we're done with our dimensional analysis, we don't want milliequivalents per hour, but we need milliliters per hour. So what we need to ask ourselves is, do we have a conversion between milliequivalents and milliliters? And the answer is yes. The milliliters is talking about the volume of the NS. And we know the strength of milliequivalents, the ratio of milliequivalents to milliliters. So you can multiply by a conversion factor where we go from milliequivalents into milliliters. And this is the strength of that bag. That bag has 1,000 mLs, and there are 15 milliequivalents in that bag. So by multiplying by 1,000 over 15, what we see is the milliequivalents will cancel, and I will have milliliters per hour. So I'm going to multiply the numerators, and I'll get 4,000. I'll come down here, right? This is equal to 4,000. 1 times 15 is 15. So when we put that in our calculator, we get 266.6 repeating, which when I round that, I'm going to round that to 266.7. We round that to the 10th place because we're dealing with a pump. So 266.7 milliliters per hour. This is what we have to set the pump for in order for the patient to be receiving 4 milliequivalents per hour. The difference in these problems compared to some of the conversions and dosage calculations that we've been doing is we're converting one rate into another. And the rate that we are given is typically a ratio of some amount of a drug, whether it be in milliequivalents, whether it be in milligrams, micrograms, or grams. Sometimes we'll see milliunits, which is similar to milliequivalents. It's a ratio of some amount over time, and that's what needs to happen. But we need to convert it often into a ratio of volume per time because it's going to be a pump. Or in the next example, a gravity set where we are pushing that medication into the patient. So this is called a rate conversion. Let's look at another example. In this example, we're told a client is to receive 11 milliunits per minute of oxytocin, and this is through an infusion, and this is going to be through a pump. The order states that we have oxytocin available 45 units, and that's mixed in 1,000 mLs of lactated ringers. We need to determine the number of milliliters per hour to set the pump. So thinking about what we just saw on the last page, the last example, is the patient has been ordered to receive a ratio, or in this case, a rate of medication. And specifically, the patient needs to receive 11 milliunits per minute of this oxytocin. So 11 milliunits every 1 minute. What we're going to be doing is setting the pump because these milliunits are floating around in this 1,000 mLs of lactated ringers. So it's going to be floating around in this bag. The bag's going to be hooked up to a pump. So what we need to do is to set the pump for a milliliter per hour rate. So what we need to do, and I'm going to make a plan here, is I need to convert, very clearly I obviously need to convert minutes into hours. That's not going to be too bad. But I somehow need to convert milliunits into milliliters. And this is where, in the last example, we used the strength of the bag. And if I look at the strength of the bag, I see 45 units in this 1,000 ml. So this strength is not a direct conversion from milliunits to milliliters. However, this idea of milliunits and units is very similar to what we saw with Milli equivalents and milligrams and grams. These are metric units. So what I can do is actually convert first, I can convert milliunits into an equivalent number of units, and then use the strength of the bag to convert that into milliliters. So let's do that. Let's first change, in this example, again, I'm changing milliunits into units because that's what is in the bag. It's what's floating around in the bag. So I'm going to do that. So I need to multiply by a conversion factor of milliunits to units. You might be thinking, I don't know that. And the answer actually is you do. You do know, you should know the conversion from a millimetric conversion to the basic unit. We know that one basic unit contains 1,000 milliunits. Very similar to milligrams and grams, milliliters and liters. And now if I use what's on the bag, I see that there are 45 units contained in 1,000 mLs. So by multiplying now by 1,000 over 45, I have converted my milliunits into an equivalent number of milliliters given the strength of this bag. The last thing to do is to now change the minutes into hours because we're setting a pump. And I know there are 60 minutes in 1 hour. So I'm going to bring this work down here. I'm going to multiply all the numerators. And when I multiply 11 times 1,000 times 60, I get 660,000. Whoops. So 660,000. When I multiply 45 times 1,000, which are the denominators, I get 45,000. And now when I put that in my calculator, I get, this is equal to 14.6 repeating, and this is milliliters per hour, and we know we're setting a pump. So rounding this to the 10th place, I get 14.7 milliliters per hour. So very briefly, just reflecting back on this problem and the previous problem, we have medication floating around in these bags, and oftentimes the order gives you a lot of information, but the most important part is what is the rate that the medication needs to be going into the patient. So in the previous problem, we had a ratio of milliequivalents per hour that needed to happen. In this problem, we have milliunits per minute that need to happen. And what we need to think about is, how is this getting into the patient? In the previous problem, it was with a pump, and in this problem, it's with a pump. so we need to convert that to milliliters per hour. You should also be able to, if necessary, if you're using a gravity set, use the tubing calibration to convert into drops per minute. So that's also something we will see.